Hi, and welcome back to Codex. Our speaker today is Jameson Cahill, who is an assistant professor in the Department of Mathematics and Statistics at UNC Wilmington. Jameson is known for his use of algebraic geometry to solve fundamental problems in frame theory. Today, he will tell us about max filtering. Take it away, Jameson.
Okay, so thanks a lot for the invitation. So this is work that I have done fairly recently with two of the organizers of this seminar. So this was with Joey and Dustin, and then Dustin's student, Dan Packer, who particularly did a really good job with helping us with some of the numerical experiments in this project. Okay, so the paper is called Group Invariant Max Filtering. It's been on arXiv since I think the end of May, so it's still pretty recent. So everything I'm going to talk about today basically is in that paper. There's also a bunch of stuff in that paper that I'm not going to talk about today. So if you're interested, it should be pretty easy to find on arXiv. Just look up any of us. And what is happening? Oops. Okay. Okay, so just to get going here, this is a diagram of the architecture of some fancy neural network. I believe this one is called AlexNet, and it's won a bunch of competitions or whatever. The point that I want to get across with having this picture as the first slide is that, you know, we hear this term big data a lot, or we have heard that a lot. And the idea with that is, in this kind of modern information age, we have access to tons and tons of data. And when you have such large amounts of data available to you, you can train some very sophisticated models that can perform a lot of tasks very well. But in order to train such a sophisticated model, you do indeed need to have access to a gigantic amount of data to use to train it, just because there's so many parameters in a model like this. But and it also requires a lot of computational power. But certainly, if that's the realm in which you're working in this day and age, you know, these really fancy neural networks can accomplish a lot of machine learning tasks very well. But a lot of times still, even in this day and age, there are a lot of problems, data kind of problems, where you really don't have access to all that much data. And you still want to be able to say something about the data set. So this is just an example of a relatively small data set here. Here you see there's 28 images of different textures. And the data set under consideration here has, I think, 150 or 160 examples of each texture. And one problem that you can imagine is trying to take this set of images and classify them into the correct textures for each image. But in this setting, if you're restricted to working specifically with this data set, you do not have enough data to train a model like I had on the previous slide. So you're going to have to do something else. So what some people do is they would just kind of include this data set along with a whole bunch of other images in data, like a larger data set to train a model like the one on the previous slide. Another thing people commonly do is what's called data augmentation. So it's like when you don't have enough data, you kind of generate a bunch of fake data using the data that you have to give yourself supposedly more data. And that's an interesting topic in how you go about doing that. But what I want to talk about today is to try to exploit some type of structure that may exist in the data itself in order to kind of get more out of the limited amount of data that you have. So if you're just looking at these pictures here, some of these textures look obviously very different from each other, just to your eye. Some of them are kind of hard to tell apart, even just like us by looking at it. But you can imagine that there's a certain amount of symmetry in this data set. Like if I took an image of a texture and I kind of just moved it over a little bit, well, that's going to be the same texture. It's not exactly the same image because it's been moved, but it's should be the same thing. Or if I kind of rotate it, that should give me the same thing. So there's certain types of symmetries at the very least that I want to be able to identify when two images would be related by that kind of thing. So what we're going to talk about today is basically considering symmetry that exists in data that will arise as some type of group action on the data set that is kind of fixed by your data, or that your data is fixed by the action, and the kind of classes of the data are preserved by that action. So here's just some basic terminology just to get us started. So I'm going to suppose I have a group G acting on a vector space V. Right now, I'm being pretty vague about what G in V can be, but later on it will be a bit more specific. So I will use the notation square bracket X to denote the orbit of a vector in V. So that just means all of the other vectors that you can get to by starting from X and letting the group act on that specific vector. And then we're going to be considering functions that have certain properties with respect to this action. So if I have a function that sends my vector space V to some Euclidean space Rn, I say that function is invariant to this action. Basically means when you plug in two vectors in the same orbit, they give you the same output, right? That's what invariant means. So that means that the function is constant on orbits. I will also say that the function is separating if when you give me two vectors that are not in the same orbit, that they give me different outputs. So a function is invariant in separating if it's always gives you the same output when you plug in vectors in the same orbit, and then that's the only time that you get that output, right? So we're going to denote the space of orbits by V mod G. So that just means you kind of mod out by this group action and you identify each vector in V with its orbit under this action. Now, there's one little subtlety I need to point out, and I'm going to point it out, and then I'm not going to really worry about it for the rest of the talk. So when you have a function that's, well, even invariant, since it's constant on orbits, that kind of induces a new function on this quotient space V mod G, right? So technically speaking, the domain of F is V. But since if it's invariant, whenever I plug in two vectors in the same orbit, I get the same output. I can kind of think of it as a function on the space of orbits. But that's technically speaking is a different function because it has a different domain. And from this point of view, that function, so here I'm calling that F tilde on V mod G, and then that will be separating F will be separating if and only if F tilde is injective at the level of orbits. However, as we go forward in this talk, all of the functions that we're going to be talking about will always be invariant. And I'm going to be a little bit loose with whether I think of it as a function of a vector or a function of the orbit of that vector, because it doesn't really matter. And sometimes it's more convenient to think of it one way versus the other. So I'm not going to be putting these tildes all over the place for the rest of the talk. So just to kind of put this back into the context that we were just talking about, the idea is that I have some vector space where my data is living, and I have some group that acts on that vector space, and that group action preserves some structure in the data that I want to have preserved. So if I have an invariant map or a separating map, I can apply that mapping to send me to this invariant space where now I'm kind of in the space of orbits per se. And then in some sense, you've kind of modded out by some information already, right? So if this mapping is well behaved enough, and I want to carry out a classification task, say by now assigning labels to things, hopefully this can be an easier task to accomplish by passing to this invariant space in the first place. So just to be clear though, in the kind of machine learning pipeline that we're talking about here, the functions that I'm talking about, these are just kind of either like a pre-processing or a measurement process or something like that. After you've processed the data in this way, you still need to run whatever kind of classifier or whatever it is you would be doing anyway. So I'm mostly going to be focusing on the first arrow in this picture. So how to give me get my hands on a good mapping from the raw data space over to the space of orbits. But we will near the end also discuss briefly like how you go do this second arrow also to get to the label space from that. Okay, so now that we've kind of motivated this concept of thinking about these invariant and separating functions, I want to just briefly talk about the history of this kind of thing, because this notion actually goes way back, and it's very deeply rooted in or a lot of the kinds of math, or just the way that we think about math nowadays has ties to people thinking about problems similar to this from a very long time ago. So I've listed some names of some famous people that everybody's probably heard of, and the years that they wrote papers on this topic. So in particular, by the time Hilbert started thinking about this in the 1890s, he had this notion of this ring of invariant polynomials. So if you think of a polynomial ring in a bunch of variables, and then you kind of think about the group, the way that the group acts maybe can kind of be permuting the variables, although there could be other types of group actions as well. And anyway, if you have a group acting on CD, then you can talk about the set of polynomial functions that are invariant in the sense that I had on the previous slide. And way back then, people like Hilbert and Emmy Noether and a bunch of other people were very interested in kind of studying the algebraic structure of this ring of invariant polynomials. And in fact, them studying that led to what we now know of as commutative algebra and algebraic geometry. These were kind of the first things that people were thinking about. So Emmy Noether eventually proved that this thing is finitely generated as an algebra over the complex numbers. I'm not going to spend a lot of time talking about what that means, but at the time, that was a big result. What that means now, though, for me, looking back, so this thing that I have as a theorem statement here, probably Hilbert or Noether wouldn't have made this statement, but this is what I care about in my modern context looking back, that this ring is always finitely generated. So now if I have a finite group, and this can hold for groups that are not finite also, but certainly definitely true for a finite group, then I can take this finite number of polynomials that generate this thing and produce a map that separates the orbits of this action. The one drawback here, though, is this capital N. So the number of polynomials in the generating set, that can be really big, even for fairly simple looking group actions. Okay, so now flash forward about 100 years, and kind of at the end of the 90s, early 2000s, these people started looking back at this notion of these invariant rings of polynomials. And by now, like by then, people were starting to think, oh, maybe this could actually be useful for kind of some computational problems, because it's kind of clear that if you can understand, these have these separating things under a group action, like I was talking about at the beginning, there's a plenty of kind of possible machine learning kind of applications. So only then did they realize that if your goal is only to separate orbits of the action, you in fact do not need to have a full generating set of the entire ring of invariant polynomials. In fact, you can get away with much fewer. So this theorem here tells you if you have an action on CD, you can always find a separating set of at most 2D plus 1 polynomials, whereas the generating set of the ring of invariants could be arbitrarily large. This is linear in D, and so that's a pretty small number. There is this one little subtlety that I want to point out here. If you do go and read any of the literature on this problem, the way the algebraists use the word separating is slightly different from the way that I've been using it here. And that's what this definition of separating set says. So if you read this, it's like you have a bunch of polynomials are called a separating set if whenever those polynomials evaluate the same for two different points, that implies that every invariant polynomial evaluates the same. What that means is that this set of polynomials separates as well as polynomials can separate. It turns out that especially when the group is not finite, that's why I had that assumption of finite before, there can be actions where there are orbits that can't be separated by polynomials. So we're not going to encounter that today. So I'm not going to dwell on that any longer, but just pointing out that subtlety. And I do want to say this notion of separating sets of polynomials is something that's being fairly actively worked on by a decent sized group of algebraists even right now. So if you go type in, yeah.
So are there bounds on the degrees? I mean, it's bounds on the
Yeah,
numbers
I mean,
of
that's
polynomials.
one of the big problems people
Yeah.
work like over there talk about is bounding the degrees of these things.
Mhm.
But that's, yeah, I'm not gonna talk about that here. So the main point that I want to make though is that you go from finite to very linear in D, right? That's kind of the, because what I'm going to be talking about, I'm more worried about the number of measurements that you need to have. So just as a quick example, let's consider the cyclic group of order 2, which I want to think of as plus and minus 1 with the operation of multiplication, and then acting on CD by scalar multiplication. So that means that the orbit of a vector x is just x and minus x. Then if you consider the nonlinear mapping that sends a vector x to its rank 1 outer product matrix, x times x transpose, it's really not hard to convince yourself that this is a invariant and separating mapping for this action. And if you look at the entries of this of x transpose along the diagonal, you get the entries of x squared. So for each xi in x, that gets squared, and then on the off diagonals, you just have the product of two distinct entries. So technically, I guess I could say I less than j because xi xj is the same as xj xi. But nonetheless, the point, like these are polynomial, they're actually monomials, and then they do in fact form a separating set in the way that I was describing in the previous slide for this particular action. This has more than 2D of them, but that still is a separating set for this action. So I want to now put a little bit more structure on this set of orbits of my group action. So I want to define a metric on this space. So if I have two orbits in this V mod G space, I want to define the distance between them as the infimum of all possible distances between a vector in X's orbit and a vector in Y's orbit. Now, there is also, it is true that there are cases where this thing does not define a metric. That's another subtlety I'm just going to kind of ignore, because in the cases that I'm going to be talking about, this is always going to be, in fact, a metric. And that will be the metric that we use. And then once I have this notion of, like I've equipped this V mod G with this metric, then I can talk about what does it mean for a function to be bilipschitz with respect to this metric. And that's what I have down on the bottom. Notice here this kind of, I'm abusing the notation in the way that I said before. Like F itself is taking in an X and a Y, whereas the distance is on the orbits of X and Y. So F itself will not be bilipschitz in this sense, because it's not going to be injective, because it's sending an entire orbit to the same thing. But I don't want to just have to play around with sticking these tildes and brackets everywhere. So for me, I'm just going to say this thing is bilipschitz on the quotient space when I have these upper and lower bounds. And the lower bound in particular here, this is giving you a more numerically meaningful notion of separating the orbits, is kind of why we care about that. Okay. So looking back at the example of the, C2 acting by scalar multiplication, if I now just let f of x be this x transpose, well, the distance, the metric for this action is just the min of the norm of x plus y and the norm of x minus y, because the orbits of these things only have two members. And then the other four, each x and y has two members of its orbit, so there's four pairs, but the other two are just the negative of those ones, so that doesn't change the distance. So if you have a unit vector u and a positive scalar c, if you calculate the distance in this quotient metric to between the orbit of 0 and the orbit of c times u, you just get this positive scalar c. But if you do this after you've applied f to it, you get c squared. So that is a pretty standard exercise that is not a bilipschitz mapping. When I say not bilipschitz, I mean it doesn't have either the upper or the lower bound, right? Kind of for different reasons, right? As c gets big, fails the upper bound, and c gets small, fails the lower bound. But you don't get either the upper or the lower bound here. So even though this map is separating, it's not bilipschitz. And in general, like whenever you have nonlinear polynomials, they're not going to be bilipschitz. So if you want bilipschitz things, this kind of looking around in polynomials is not necessarily the way to go. Okay, so now I'm going to talk briefly about this problem called phase retrieval, and this is kind of the perspective at which I came at this kind of problem, which is why I'm talking about it. So, because this is like my own background, back when I was a student in a postdoc, I wrote a handful of papers on this topic, and it can be viewed as a special case of the problem that I'm considering here, although we didn't really think of it that way back then. So if you have a collection of vectors in CD, we say that those vectors do phase retrieval if whenever you have two vectors x and y such that the absolute values of the inner products with everything in my list of vectors are the same, then that means that x has to equal lambda y for some scalar lambda with modulus 1. Certainly, if you have x equals lambda y then that absolute value equation is always going to be true. So you can never get around that. But it turns out, depending on your choice of these vectors phi I, there could be other X and Y pairs that satisfy that equation. So, and then if we're working over the real numbers, we only care about plus and minus 1 instead of all possible complex scalars of unit modulus. So now phase retrieval itself was the name of it is really like, how do you recover X up to a global phase factor given measurements of this form? But if you want to be able to do that, you have to understand what do the measurements need to satisfy in order for that to even be possible to do. So from that perspective, what we can think of this as saying the mapping that sends X to this list of absolute values of inner products separates the orbits of the action of either this torus acting by scalar multiplication in the complex case, or again, this cyclic group of order 2 acting by scalar multiplication in the real case. And the observation to make here is that these absolute value functions, they are not polynomials. They're kind of almost not that far off from polynomials, but they're not polynomials. And you know, there's a lot more I could say about this, but right now I just want to get the point across that this is a problem that can be formulated as asking to separate the orbits of this specific action. And then here's a theorem that is a conglomeration of a whole bunch of theorems proved by some of them by me, some of them by other people over the course of a series of papers. But the point here is that if n is big enough, and n was the number of vectors in my list, then choosing those vectors generically, you'll get a set of vectors that does a phase retrieval. And whereby big enough, I can say bigger than 4D minus 4 in the complex case, and bigger than 2D minus 1 in the real case, where D is the dimension, again, of the underlying space. And by generic, what I mean is basically that there is like the set of choices for which it doesn't work is kind of lying on a lower dimensional subset. So it's kind of like a tiny sliver of things that will not work. And then as long as you pick something off of that tiny, tiny little sliver, then it's going to work. And then the other point is that whenever you get injective here, you automatically get bilipschitz with respect to this quotient metric in this case. And again, you know, this was a bunch of different theorems being condensed down into one, but this is kind of the way that I think about these problems because I have this background. So just to make it clear, now returning to the more general case, I'm going to have a group G, and what I'm going to be talking about here today is always going to be acting on like a real Euclidean space. RD, like a finite dimensional real Euclidean space. So I want to have functions that do these things, right? At the very least, I want it to be invariant and separating, which I've talked about already. But in reality, I'm using these words stable and robust. That's basically just saying bilipschitz in the way that I've defined it. So you can think of these upper and lower Lipschitz bounds, like I mentioned, as kind of giving you more numerical versions of invariant and separating. And then I want it to be what I'm calling user-friendly here, meaning that it's an easy function to compute, because I don't want something that's impossible to actually compute. And then, you know, when you implement it, it shouldn't get a lot of crazy numerical errors. And then also I want the target dimension n, where I'm sending everything to be as small as possible. So like when I was talking about this notion of separating sets, you could always get into a dimension of 2D plus 1. And just on the previous slide with phase retrieval, In the complex case, you could always get to 4D minus 4, and in the real case, 2D minus 1. So in all of these cases, you're ending up in a dimension that's linear in the dimension where you started out. And so, like, if that's possible, I would like to have that. Okay, so finally, getting to the actual new thing here. This talk is called max filtering, and this is the thing that we decided to work with here. So if you give me any group at this point of linear isometries acting on, right now I'm just saying a real inner product space, but again, that will mostly be a finite dimensional real inner product space. Then we define this max filtering map to be, if you take the max filter between the orbit of X and the orbit of Y, what that means is you take the supremum of the inner products amongst all vectors in the orbit of X with all vectors in the orbit of Y. And again, this last sentence here is just pointing out this ambiguity, whether you think of it as a function on the orbit or as a function on the vector itself. And we're not going to bother making that distinction. Now, one thing to notice here is that as long as this is well defined, it's definitely invariant on the orbits, right? Because it's just defined in a way to be invariant, because you're just scrolling over the entire orbit to get your output. Now, since I'm assuming that this is a group of isometries, and that means that the adjoint of anything that's in the group is also in there, because the adjoint is the inverse, since they're isometries. So that means that inside of the inner product, in principle, I have an element of the group G acting on both X and Y, but I can push one of them over to the other side of the inner product, so that I only have to consider the group acting on either X or Y inside of this inner product. And when the group is finite, or at least just like a topologically closed, so a compact group in what we're going to be talking about going forward, the soup can be replaced by a max. So this last line that I have on this slide here, this is what I really want people to think about as max filtering. So you have a group action, and you take two vectors, and then the max filtering map between the two orbits of that vector is the max of Gx inner product Y, where you max over G, okay? Which is the same as saying max of X inner product Gy, max over G. Okay, so that's the real mapping. This last line here, that's what I have in my head whenever I think about max filtering. So we got to make up this, we had to make this symbol of this double wrangle in LaTeX. So how often do you get to do that? And then we get to prove one of these things that you see in like chapter 1.1 of every like undergraduate math textbook. So I'm not going to go line by line through this thing, but this is just saying that max filtering is a pretty well-behaved mathematical object. I want to specifically point out property C here, which says that you can pull positive scalars out of this map. That means that this is a homogeneous mapping. So even though it's not a linear mapping, it still has this homogeneity property. And one thing that allows you to do in many instances is to scale everything down so that you're working inside of a ball. And then you can put yourself into a compact set if that's a convenient thing to do, for example, which it often is a convenient thing to do, and then just extend out radially once you know what happens inside the ball. I'm also will make reference later on in this talk to properties F and G here. But anyway, this is just one of these list of properties. This slide is not saying a whole lot. It's just saying when you stack a bunch of max filters next to each other, then we call that a max filter bank. We also use the word template to mean if we're fixing like one of the vectors that we're max filtering against. So it's like this max filter bank. It's kind of like the analysis operator of the frame of these ZIs for people who know what that is, except for you're taking max filters in each spot. So the kind of questions that we want to ask, first of all, is like how big does my max filter bank have to be to separate and or to get bilipschitz and kind of stuff like that. A single max filter is not going to do that. It's invariant, but it's like you need to stack a bunch of them next to each other to get these other properties. So basically, max filter bank is the word that we use for a bunch of max filters. One thing I want to just point out very quickly here, I've defined this for real inner product spaces. However, if you have a complex inner product space, you can associate that with the real space of twice the dimension. And then the real inner product is just the real part of the complex inner product. So then if you have a bunch of unitary matrices acting on CD, well, that actually, you can think of that as a subgroup of the orthogonal group of the corresponding real inner product space. So the point of this is just to say that like we do, even though we're saying real inner product space all over the place, we capture this notion of unitary actions on complex spaces along with this. But we just have to think of it in this way. So we're not leaving out these unitary actions, which many times those are what in fact we care about. Okay, and then just to make sure it's clear, in both of the two, like the phase retrieval case. So now, I was calling this group the torus before, but now to think of it as a group of matrices, I just think of it as scalar multiples of the identity. And then that will act on CD effectively as multiplying by those scalars. And then the cyclic group of order 2, I now think of as plus or minus the identity matrix. And then in either of these cases, the corresponding max filter gives you the absolute value of the corresponding inner product. So what that means is phase retrieval is in fact now a special case of this thing. So this max filtering is an honest generalization of phase retrieval. Okay, so here is the first main theorem that we had. So it's kind of wordy. I was debating on, do I want to kind of strip out a lot of the words here, but I decided to leave it as it is. So this theorem here is telling you that when you have a finite group, a finite subgroup of O of D acting on RD, then as long as you take enough templates in your filter bank, then with high probability, the corresponding max filter bank will be bilipschitz. So as far as we know, this is the first result of this kind at this level of generality that shows that you can always embed this space of orbits with a bilipschitz mapping into a Euclidean space. There are some things that are not completely optimal here. If you stare at this for long enough. So the lower Lipschitz bound is this delta thing. And if you look at this delta in this display, delta does not actually depend on n. N is the number of measurements or templates that you use. So by adding more measurements to more templates to your filter bank, at least in this theorem, you're not increasing the lower Lipschitz bound, which is kind of weird. Also, the dependence of n on m and d is probably not optimal. On the other hand, we're working at a pretty high level of generality here. So when you're proving a theorem like this, you're never going to be able to get better than the worst possible case, right? So we're proving something that holds for all finite groups. So I guess you shouldn't really expect to have that great of a result at something that general, right? If you want to get better bounds here, you probably have to have a specific kind of group action that you look carefully at. Like Dustin and I have a paper from about a decade ago now, where we did this specifically for real phase retrieval, and we got pretty decent bounds. So if you have a specific group action in mind, you can probably look through this and or do something kind of like this and get a much more precise result. And then, yeah, I don't want to go into details about how this proof works. But just the upper bound is easy. It just follows from the lemma from a few slides ago. The lower bound, there is room for improvement here. It follows from some property we called projective uniformity. There's a place where we kind of use a pigeonhole principle, though, and we do give up quite a bit. So even though this is a fairly general theorem, there very likely is some room for improvement here. But anyway, this was our first result. Once we got this, we were kind of in business here. Now just going on to the next thing. So that thing told me about separating, and depending on what the group was, I would need kind of a lot of measurements or a lot of templates in my filter bank. This thing, this result here is telling me that for any finite group, I can get away with separating with only using 2D templates in my filter bank. So the story here, we were like almost done with this paper, and we did not have this result. And then this other paper that I'm pointing out here, Low Dimensional Invariant Embeddings for Universal Geometric Learning by Dim and Gortler, popped up on the archive like while we were in the process of writing our paper. And then we somehow got our hands on it, and then we realized it's like, wow, they have a pretty ridiculous set of hypotheses here, but we happen to have this exact thing that plugs right into their theorem. So, so we got this separating result here, which basically follows from them. That their result gave the number that we needed as 2D plus 1, which is the exact same number that we get from the algebraic separating sets that I had way back at the beginning. But we leveraged the fact that we have this homogeneity property to knock off an extra, that plus 1. So the natural question here is, we can separate generically with 2D, and we can get bilipschitz with high probability with, just go back here with this thing, 12m squared d, and then log of this other thing that depends on m and d, but like m squared d basically. So you have this order of the group squared multiplying d, so there's a gap in between these two things in general, right? So a natural question is, just like in phase retrieval, I had this result that said as soon as you separate, you always automatically get bilipschitz. So we don't have a proof of that here yet. We expect something like that might be true. But right now we have two separate statements for separating and bilipschitz. Okay, I think I'm going to skip that in the interest of time, since I'm almost out of time. So I want to briefly discuss the complexity of evaluating a max filter. So like if you just look at the definition on its face, well, in order to compute the max filter between two orbits, you need to scroll through the entire orbit and compute an inner product like X inner product GY, and just evaluate that for every G in G. And if M, the order of G, is big, that can be a prohibitive thing to do. But in general, because of this relation between the max filter and the quotient metric, the max filter is as easy to compute as the quotient metric is. So there are instances where we have some examples where you can compute it, compute the max filter faster than just scrolling through all of those things. So, and there's kind of a lot on this slide. Maybe I will just talk about this one here. So if you have the group of cyclic or circular translations, so if you're in a finite dimensional space, and then you translate, but you kind of wrap back around at the end of the vector. That's a very important group action in a lot of kind of machine learning applications. So if you want to max filter that thing against that action, it turns out that you're basically taking a max of a convolution. So if you want to max filter F with G, then you basically, what you need to do is take the convolution of F with the reversal of G. That R just means reversal, and it just means you write the vector backwards. It just shows up there for whatever reason. And then using the FFT, you turn convolution into regular multiplication. So you can take the FFT of F and G, take the pointwise product of that, and then take the inverse Fourier transform, and then just take the maximum entry of that. And then that is pretty fast. So then you don't have to scroll through every possible translate of G and take the inner product with F. So I think I'm basically out of time. So I just have a list of problems here. Maybe I'll just kind of put this up and take any questions that anybody has at this time.
See, I have a question.
Yeah.